Hello everyone. In this project, predicting electrical energy output using machine learning, I have developed a learning model to predict the early electrical energy output of a combined power plant. The objective was to use the historical environment sensor data to accurately estimate the plant's net electrical energy generation. Accurate energy prediction helps our plants improve operational planning, optimization, and making informed decisions. The data set initially contained over 9,700 observations. After removing the duplicate records, I worked with a clean data set of 9,527 observations. The input features include ambient temperature, ambient pressure, relative humidity, and exhaust vacuum, while the target variable was the net hourly electrical energy output measured in megawatts. So this data set had input features and the output target variable, which has 4 input features and 1 target variable. This So from the approach perspective, modeling approach perspective, this project is a supervised machine learning problem because the historical data set contains both the input variables and their corresponding output values. Since the target variable electrical energy output is a continuous numerical value, this is a regression problem. I've used all the 4 environmental variables as a model features because they directly influence the efficiency and the power generation of the plant. Before building the models, I've performed the basic data preparation by checking for the missing values and removing the duplicate records. I then split the data into 80% training data and 20% of the testing data. To obtain a reliable estimate of model performance, I used 5-fold cross-validation during model training. To identify the best predictive model, I compared the 2 machine learning algorithms. The first was the linear regression, which served as a simple baseline model because it is easy to interpret and commonly used for the regression problems. And the second was a random forest regression, which can capture more complex and non-linear relationships between environmental conditions and electrical energy output. I've evaluated both models using the 5-fold cross-validation and compared their prediction errors. Using the RMSE, the model with the lowest validation error was selected as a final model for the evaluation on the unseen test data, which is After comparing the models, our random forest regression achieved the best performance and was selected as the final model. To evaluate the model, I used 3 standard regression metrics through RMSE, mean absolute error, and R-squared score. RMSE measures the typical prediction error in megawatts. MAE represents the average absolute prediction error, and R-squared indicates how much variation in electrical energy output is explained in this model. As shown in this slide, the final model achieved an RMSE of 3.328 megawatts. MAE is mean absolute error is 2.329 megawatts, and test R square is 0.962. The results indicate that the model is able to accurately predict electrical energy output on the previously unseen data, which is also, we are calling it as test data. This table represents several sample predictions generated by the final model using the test data set. Each row contains environmental conditions and the actual electrical energy output. The model has predicted the output and then absolute prediction error. For example, in the first observation, the actual output was 463.57 megawatts, while the model predicted 464.68 megawatts, resulting in an error of only 1.11 megawatts. Across these examples, the prediction errors remain relatively small, demonstrating that the model is generalizing well and producing predictions that are close to the actual plant output. In conclusion, the project has successfully demonstrated complete machine learning workflow for predicting electrical energy output using historical environment data. Thank you very much for watching. I appreciate your time and thank you for giving me this opportunity.